All right, his work has been honored with a number of awards, including most recently the William Grove Award from the International Association for Energy. Very excited to have you here, Dr. Weber. So without further ado, the floor is yours. Thanks.
Thanks for the introduction, and thanks for inviting me to come out here today. It's nice to actually be somewhere back in person. And so that's always a nice feeling. Some normalcy in life here. So what I was going to talk to you today about is the importance of transport and electrochemical energy conversion technologies. So as David mentioned, I'm from Berkeley Lab. For those who don't know, this is a view of San Francisco. This is the advanced light source that you can see here. And so we sit right above that campus. And so then the question is, why are we focused on electrochemical energy technologies, and what are we really trying to get through? And so if we look at really the energy mix within the US, and especially looking at the carbon dioxide emission scenarios, it's really, we see here places like hydrogen can really decarbonize the hard to decarbonize sectors. And so a couple of these are things like manufacturing, things like long haul transportation, eventually things like if we go off onto ammonia and green ammonia production as well, and chemical industry. And so where we work is kind of two sectors here. One is this Million Mile Fuel Cell Truck Consortium. And so that's very much focused on looking now at kind of more heavy duty type applications for fuel cells. And so that's moving beyond kind of what we've done, for example, in light duty and forklifts, to applications where you're at much larger ranges, much larger sizes. And so you kind of change a little bit your CapEx versus OpEx optimization. So things like efficiency, durability start to become more and more important than just pure performance. And so some of the targets are shown on the bottom table, showing when you're going from light duty to heavy duty applications, what you really have to go after in terms of some of these increases. The other kind of thing that motivates us is something we call the electrochemical refinery, or kind of power to products, to where, if we look at our traditional systems shown here on the top, is very much a thermal chemical industry. And we see the future, especially with renewable electrons, to be really electrochemical conversion and electrochemistry focused rather than thermally focused. And so shown here is just a quote from Harry Gray from Caltech, arguing that electrochemistry is poised to be to the 21st century what thermal chemistry was to the 20th. And so as we start to go through and look at these different technologies, we need to start thinking about, how do we optimize this future of electrochemical conversion? So in that spirit, this is kind of an outline of what I'll talk about today. I'll look at, kind of an overview of porous electrodes, looking at mass transport and what we call kind of fuel cell-like or fuel cell systems. Then do 2 case studies and focus very much on kind of transport, mainly at kind of the very local or catalytic level. So the first one will be low platinum loadings in fuel cells. The second case study will be looking at CO2 reduction, specifically with gas diffusion electrodes. So starting in, first, why fuel cell-like systems? And so this is just an overview of the energy conversion group that I lead. So my group is part of that, as well as 3 other PIs within our division. And really what we focus on is kind of energy conversion and focus basically on electrochemical energy conversion. So looking at things like low temperature electrolysis, looking at things like fuel cells, reversible flow cells, touching on some manufacturing, touching on things like CO2 reduction. And really what we see is at the end of the day, a lot of these start looking very similar in terms of their architectures and what we want to do and what they need to accomplish. In addition, what we focus on in our group is not a lot of synthesis necessarily, but a lot more on the diagnostics, the characterization, and modeling to really understand how different systems actually operate. And that's kind of what we want to focus on as a group. Our kind of tagline is doing this fundamental systematic research, but to solve applied problems. So as I mentioned, when we start looking at these technologies, shown here on the left is a PEM fuel cell. So here you have systems that have very thin membranes. These membranes are ion conducting and they don't allow electrons through. You have thinner catalyst layers on both sides to do your reactions. You usually have some kind of support material to help disperse reactants and take away products. And so the fuel cell architecture, you see it replicated here. This is a hydrogen bromine flow battery. We see it here in a CO2 reduction device. We even see it kind of here in a solar photochemistry, water splitting device, or in a water electrolyzer shown all the way on the right bottom. And so once again, if we start to understand one of these architectures, we should be able to bring it to bear to a lot of different types of technologies. If we look now specifically at transport phenomena, these are very hierarchical structures. And so you have stacks of single cells. Those single cells have those components that I kind of just showed on the previous slide. And if we delve into even more detailed into nanostructure, we have transport that occurs on the thousands of nanometers all the way down on kind of the single nanometers to where we actually are having our catalytic reactions occur. And so really what we need to understand is how all of these disparate lengths and eventually time scales actually interact with each other. So if we delve a little bit more into the fuel cell specifically, so once again, looking at kind of the cell architectures as shown here on the left is a little bit more of the phenomena that goes into these systems. But really what we see is it's complex in terms of we're trying to get gaseous reactants into the two electrodes and the catalyst layers where they convert the ions transport through this proton exchange membrane or ionomer. This ionomer also exists within these porous catalyst layers that kind of coat the particles. And then of course we have multiple movement of water and ions in the membranes and catalyst layers. We have multi-phase flow perhaps in our backing layers and in our porous media, our gas diffusion layer, or microporous layers. And so then, of course, we also have electron flow. And so you can see already that we have a lot of different phenomena that we're trying to get to more or less the same spot. If we now look at kind of CO2 reduction, this is kind of from a review or perspective that we wrote. And if we look first here at the leftmost points, these are really, looking at the Faraday efficiency. So how much of your electrons are doing what you wanted to do in terms of making these reactants. And this is an aqueous type cell. So this is what we would typically find was kind of the standard, maybe 5-10 years ago when we started going into the field. And what you see here is if we look at the current densities are very low that you can achieve. So although you can get pretty high Faraday efficiencies to some products, you can't necessarily get them at high rates. And so if we think of industrially scaling these systems, this is going to be problematic. And the reason that we can see that is really when we delve into the details shown here in these planar cells is we have a very large diffusion barrier of water to get to the electrode. We know that CO2 is not that soluble within aqueous media, and so this is actually going to limit our overall performance. And so that's just shown here in kind of a back of the envelope calculation of the limiting current density as a function of kind of the diffusion length, where once again, you're typically around 100 microns or so for a boundary layer. If we now move to kind of this fuel cell-like architecture or gas diffusion electrodes, what we see is we're getting these thin kind of electrolyte layers that might be liquid or polymer. What this does is allow us to go to very small diffusion lengths, which so allows us to go to very high limiting currents. So that's in theory. In practice, what you see here is now we've opened up the windows that we can go up to higher partial current densities. And we do lose a little bit on Faraday efficiency, perhaps, especially to some of the more complicated C2 products that we want, like ethylene. But we can already see here, controlling that transport actually gives us better performance and allows it to open up a design space. And so if we look at mass transport losses in general, and so first I'll start with the fuel cell, we can look at kind of the dynamics or the prototypical curve of a fuel cell is a polarization curve. So cell operating potential is a function of current density. We see that we can break this up into different components such as kinetic losses, ohmic losses, and the rest, which is kind of mass transport losses. And what we see here, like on the previous slide of this limiting current, it always has more or less this exponential type behavior because we're limiting it. So now you're going to get a lot of cell potential with not any more current. And so if we look at what we call comparison analysis, we see that the overpotentials will essentially shoot here to infinity. And so this is that signature that we can look for mass transport. If we now look at other systems, so once again, we'll take the PEM system, but we'll also here look at a hydroxide exchange membrane fuel cell. So kind of an alkaline analog of that where we're conducting hydroxide instead of protons, as well as a PEM water electrolysis unit, where here we're splitting water instead of combining hydrogen and oxygen to make water. We can do the same kind of breakdowns. And so once again, we saw this on the left already. In the middle, we can see, once again, these transport losses that start to creep into the system. And even on the electrolyzer losses, we actually start to see increased transport losses. These aren't necessarily that bad at these low current densities, but these show up more as ohmic losses that are nonlinear because of dehydration effects in the membrane. And so what we see is similar in all these architectures is kind of this role of mass transport and the way it can actually limit overall performance. So that takes us to kind of our first case study, which is looking at fuel cells at low platinum loadings, looking at the kind of the local resistance and the impact of the ionomer. So what we want to do in fuel cells, especially from performance, is to reduce the cost. And in order to reduce the cost, the most expensive component is the catalyst itself. So we want to decrease the amount of catalyst we put in. So just as a reminder here, we see kind of our sandwich of catalyst layers membrane. Within the catalyst layers, we have catalysts, which are platinum particles on top of a carbon support, which are covered more or less by this ion conducting polymer so that you can get both protons, you have void volumes to get gases or water out, and then you also have the carbon to provide the electron conduction. And so really it's this interface where the reaction occurs. So what happens when we want to decrease the amount of catalyst in the system? So there's a couple ways to do it, but really if we just look schematically here, of taking a normal catalyst layer and either thinning it out in terms of putting less catalyst, but still keeping the overall thickness, or just making a thinner catalyst layer, what we would expect is if we want the same overall current density for this whole integrated volume, for each component, we're going to get a higher flux locally, such that we can get to the average value. Now, if we get a higher flux locally, and this is resistive, or there are some local limitations, we would expect this to be exacerbated as we decrease the amount of platinum in the system. And so this is precisely what we see. So when we decrease the amount of platinum loading, this local transport resistance increases, and it increases once again, kind of almost exponentially here, such that we are getting limited now to local transport. So things we never would have thought of at kind of higher loadings, we now see are actually starting to play a big role in the system. And so this was all experimental data with oxygen. What we wanted to see is, is this intrinsic, or is this, we know oxygen's a sluggish reaction. Is this something that's just endemic to the oxygen itself? And so what we did is hydrogen and deuterium limiting current type cell setups. The similar cell, more or less, that you saw before. What we can actually then do is vary pressures, vary gases, and break out the individual contributions. And when we do that, we see that this transport resistance throughout the whole cell is really dominated by the transport in the catalyst layer. And similar to what we saw before with the oxygen, as we decrease the amount of catalyst or decrease the loading, we're getting this sharp increase in this resistance. And so this is telling us that something's happening very locally, and it's very resistive, more so than we would expect. And so then the question is, why is that the case? And so what we know is when we go to very thin ionomer films, so this is on the order of 10 nanometers or so, compared to 100 microns or 50 microns for the membrane. What we see is when we measure the amount of water in the cell, and so this is the water uptake as a function of relative humidity. And this water content really is what derives, or a lot of the transport properties are just a direct function of the water content. And so when we see it, when we do a catalyst layer, it has much lower water contents than when we do a membrane. And so this is already telling us that, not only is our flux increasing for these sites, but we also know that just intrinsically, they're going to be more resistive because they don't uptake the water as much. And that's due to kind of polymer physics and confinement effects. So kind of then to deconvolute, whether it's just transport through the film or a dissolution into the film and something going on at the surface, what we did is we changed the amount of ionomer, so the loading of the ionomer per the carbon molecules within the systems, or the I to C ratio. And so what we can do then is, as we vary the I to C ratio, we're essentially varying the thickness of that ionomer film. And so we would expect a kind of trend that would be linear if it's just purely a mass transport trend, right? We're just changing the amount of material that we're diffusing through. And so when we do that, we actually see that, yes, we do get a linear trend. So this slope of this line will tell us about the diffusivity through the ionomer. But interestingly, we also get this kind of non-zero intercept. And so this is telling us that there's something going on in terms of an interfacial effect. And so what we did is looked at two different ionomers, one with more ion exchange sites, one with less ion exchange sites. And we see that, there are changes in the actual permeability, if you will, or transport through the film. There's also changes in this interfacial intercept. So to rationalize that, we can do a few other experiments. One is to look at the water uptake based on thickness swelling of ellipsometry for the films. And so as we start to go to more ion exchange capacities, we get higher water uptake. And so that explains why we would have perhaps a smaller slope here. The other one then was to look at scattering results. And so we do a grazing incidence small angle X-ray scattering, but really this just tells us a little bit about the ionomer interaction with the substrate itself. And so when we did this, what we see is as we go to lower equivalent weights, we're getting stronger peaks, which is telling us that we have more interactions in the system. And so now we actually have ex situ experiments, mainly the water uptake here and the scattering. And these are model systems, not catalyst layers for both of these, but they're informing directly what's going on in the catalyst layer. And so now we can correlate a lot of these model studies with what's going on in the catalyst layer in terms of resistance and come up with a picture of what's actually occurring in terms of at low ion exchange capacities. So not a lot of side chains. What we have is we don't have a lot of interactions, and so we have a lower interfacial resistance, but we also have worse transport because we have worse water uptake through the film, whereas it's the opposite case when we go to high ion exchange capacities, where we have more interactions, which is detrimental, but we also have more water uptake, which is advantageous. And so this gives us some ideas of now playing with the properties and really understanding what's going on in terms of this local transport resistance, which is something that, once again, we see that it's really the transport that's limiting us and some things that we have to do. So within, for example, the Million Mile Fuel Cell Truck Consortium, we're looking at adding bulky volume ionomer components into here to create a more oxygen transport avenue and similar type results of looking at mesoporous carbons where we can vary the catalyst and then we get rid of kind of this interfacial interaction terms. So that was kind of the first case study that I wanted to go through. And once again, really focused on understanding, how transport's playing a role here. The second one is looking now at a slightly different system and looking at CO2 reduction. And so that's going towards kind of that manufacturing side of the system. And so as I mentioned, initially, a lot of what my group likes to do is multi-scale modeling and multi-physics modeling to understand the systems. And so this is just an example of the CO2 reduction half cell or cell here, where once again, we have here, we're worried about anion exchange membranes. And we'll get into that in a minute, but basically you need to operate these in acidic conditions in order to get any product besides hydrogen. In acid conditions, you're just going to get the hydrogen product. So we have a slightly different ionomer with slightly different properties. But once again, we have our gas diffusion layers, our catalyst layer, and then our anode catalyst layer as well, which we just use for this case, a planar film of iridium oxide. There's also perhaps the existence of an exchange solution, and I'll talk about that in a minute, in order to create better performance. The physics is pretty much the same. What we always look at is mass and charge and energy conservation, our various reaction kinetics, our various constitutive equations, and our momentum equations as well for the transport of the various species. So one of the interesting things is now that since we have this anion exchange membrane instead of this proton exchange membrane, what happens is this can actually interact now with our CO2. And so similarly to any basic solution, the CO2 can go into the membrane, create bicarbonates and carbonate species. And this is going to limit performance. We know that it changes the membrane properties, but it can also, be an issue in terms of getting the CO2 to the surface that I'll mention. We're doing a CO2 electrolysis. So on the anode side, we're doing oxygen evolution. On the cathode side, we actually have a variety of different reactions that we can go after. Some of this is going to depend on the catalyst, but as you'll see, a lot of it also depends on what that local reaction environment looks like and what the actual mass transport to that environment is. So just to highlight a little bit the transport aspects of having these alkaline systems, we can do a very simple back of the envelope type calculations. Here, we're just going to take, for this case, methane and producing methane. And what we'll look at is just, we're looking at the flux. We're doing an aqueous case just for this one to look at, 100 micron or 50 micron boundary layer. And then a bulk solution that has, various salt solutions, various CO2 in the system. And so what we can do is look at a couple different buffering agents. But really what we want to do is understand the fact that, at our bulk electrolyte, we might have, close to the same pH as we would expect just from pure equilibrium of the different salts. But what we see is locally, we drive to a much higher pH. And that's because if you look at the reaction, we're producing a lot of hydroxide. And so now, even though we're talking, not that big of a boundary layer, we get a huge pH gradient across the system. So that what that does is that through our reaction starts eating up our CO2. And so we can say, well, from Fick's law, just a linear type relationship is what we would expect for our CO2 concentration. But because we're going towards these higher alkaline systems, we start eating it up more. And so we're not getting that kind of concentration distribution. So what that translates then in terms of limiting currents and current performance in this polarization curve is we can see with Fick's, we would expect this kind of relationship. But what we're seeing is we're not getting close to that. And that's due to the fact that the transport and the reaction start eating up our reactant in the system. And so this once again, kind of highlights this. And even when we go towards buffered systems, we can see the buffering helps us a little bit, but you can easily either overwhelm the buffering capacity, or it's just so local and so close to the electrode interface that the buffers just aren't getting there. And there's time scales that have to go into that as well. So if we turn back to what we do with CO2 reduction, what we can see here is, this is the same kind of polarization breakdown that I showed, the applied voltage breakdown. And once again, we see similar type of effects. So when you go towards higher current densities, you're not getting as good a performance. You're getting more of the hydroxide. But furthermore, if this is a full system, you start to become water limited. And so this is just our simulation of what the water content's looking like at different current densities. We're seeing it being brought down because of the fact we're moving water as both the reactant, and it moves by electroosmosis to the other side of the cell. And that actually changes as well with the bicarbonate and the OH concentration at the higher currents. We're just more in hydroxide, which then will actually eat up some of the CO2 more. So once again, looking at back of the envelope calculation, what we actually see in this system is when we move from a planar system to a MEA or GDE system, we know that we're going to be able to get to higher current densities. We've already talked about that because of the smaller diffusion links. But what we actually see here is now we're starting to become water limited. So if we just estimate what limiting currents would be in all these different cases, we see that it's really the water is what's limiting us. And this is just, at ambient conditions. So then we can think of, well, what are other ways to do it? And so we can borrow something from the electrolysis field, which basically adds a water layer outside of the electrode. If we add it inside, in between these two electrodes, that just creates a large ohmic drop. So that's something we want to avoid. So really, we just want the water to hydrate our system. And so if we add liquid water, we can actually see that we go from the full MEA or the membrane electrode assembly or the gas diffusion electrode to a water one, we're getting better performance. As we actually add things like exchange solutions, so salt solutions and electrolytes, we can get even better performance. It maintains the local environment. It decreases any kind of Nernstein losses, which are essentially just due to the fact that you have pH gradients in the system. We can even operate even better with things like KOH systems, but these will actually have other problems, such as the fact that one, KOH is going to strongly drive and take all of the CO2 that you're feeding in, so your overall CO2 efficiency becomes down. Furthermore, there are certain solubility limits. And so if you want to go up towards above an amp per centimeter squared, you're not going to necessarily be able to do it well with these electrolyte solutions, because as the electrolyte goes over, its solubility limit's going to be reached. You're going to precipitate and then cause additional mass transport and other losses in the system. But this does show you kind of a little bit of what's going on in terms of some of these CO2 reduction and limitations in the mass transport. So similarly, that was all kind of from the modeling. This is all experimental data now. We can do things like raise the temperature. So as we raise the temperature, that also, for a full vapor cell, that increases the humidity you're entering in, because the vapor pressure is just higher with higher temperature. Also, it increases the kinetics. It also increases the transport. So usually higher temperatures is good for a lot of cases. And so we see that in terms of this polarization curve. Furthermore, as we talked before, going from a full MEA or gas diffusion electrode to a water exchanged MEA, once again, we're getting better performance due to that hydration. We're actually getting more stable performance as well, as you can see in the cycling here. And so this kind of informs us that we want to go towards these water exchanged MEAs in these gas diffusion electrodes for CO2 reduction, or even for electrolysis in general. The reason we don't do that for fuel cells is because fuel cells, both of our reactants are gaseous. And so we can't really feed in water on one of the sides. Here, the anode side is really just doing oxygen evolution. And so it's okay to kind of feed in a liquid in that side. So then, similar to what we saw before, when we started looking at some of the loading effects in fuel cells, we can say, what is the optimum type of structure when we're changing it? And so what we're going to do is change this I to C ratio. There's no carbon in the system, so it's an ionomer to catalyst ratio, but essentially it's the same amount or same concept. We're just putting in this different amounts of ionomer for different amounts of catalyst. And so if we see initially, we're getting better performance as we add in a more and more ionomer to perhaps a limit in terms of the total cell current density. We can actually then break this out. This was all done on a silver catalyst. So silver produces either CO or hydrogen. And so in fact, you can look at both either the hydrogen partial current density or the CO partial current density. Really what we want to optimize for is the CO partial current density in terms of we want a lot of CO and we want to kind of minimize how much hydrogen we get at the same time. So we have a high Faraday efficiency to CO. And so what we see here is we get kind of this optimum of this I to Cat3 type ratio. Similar to the exchange solutions that we talked about before, is we can actually add in cesium carbonate or bicarbonate as an exchange solution. When we do that, we do get better performance. But some of this, performance, as you can see here in the CO, there's a certain maximum in terms of what cell potential you want to operate. Because as you start to drive it higher or lower, you start to produce more and more hydrogen, which is essentially kind of more or less linear with the catalyst that I'll talk about in a minute, but not so much with the CO here. So that's just showing once again that the transport, that there's a trade-off when we look at this macro scale transport in terms of this ionomer to catalyst ratio that really actually drives as well what's going on in terms of what reaction we get. So that's kind of the very local transport that it drives too. So similarly, we can look, here at looking at different loadings. And so now what happens if we have any of these local transport resistances? And so once again, we do see that there's an optimum, especially in the CO partial current density. And that's due to the fact that we're getting, as we get and change the loadings, we're getting different distributions of the potential throughout the layer. So this is something we don't necessarily care about it in fuel cells because we're only making one product or only using one product. What in these systems where we have product selectivity that depends on potential, understanding what's going throughout the whole porous electrode starts to derive and change kind of what our Faraday efficiencies and which part of the electrodes are producing what. So at least in terms for the silver here of this gas diffusion electrode, we can see that if we don't have a lot of ionomer in the system, we're going to be reacting right at the interface with the membrane. We're not going to really utilize a lot of our catalyst surface area. If we have a very high ratio, we actually start to block some of the pore space. We get porous transport losses. So although we might not be as ionically limited, we start to become more gas limited in the system, as well as perhaps even electron limited if we go too high in ionomer content. And so what we see here is we get a nice kind of ratio of shown here of there is this kind of optimum in the system. So once again, just showing you what the importance of transport phenomena in the system actually is. And in terms of understanding what's going on throughout the porous electrode, especially here as it dominates things like selectivity. So in the last part of the talk, I want to focus a little bit more on this selectivity issue. And so we're going to switch from looking at porous electrodes with silver, where we only make two products, CO and hydrogen, to porous electrodes with copper, where we know we can make a whole bunch of different types of products. So shown here are the different products that we looked at. So these are the different species that we can get. Within things like the Liquid Sunlight Alliance, and before that JCAP, we're focused very much on carbon-carbon bond formation. So things like ethylene or ethanol or even larger type molecules. And really what I wanted to show is we can cover this with kind of just a simple Butler-Volmer type of expression, where really what you just need to realize is that there's a pH dependence, there's kind of a CO2 dependence, and then there's a potential dependence of each of these different types of reactions. So what we see here is the C1 products and hydrogen are very suppressed at high pH. So once again, that is why we want to go to these alkaline systems. We want to make sure that we're not in acid where we're just going to get hydrogen. We see that the C2 plus products are very independent of pH. And so if we have a way to control the pH and keep it very alkaline, we would expect more C2 products just by kind of a law of mass action, if you will. If we then go look at kind of the dependence of CO2, we see that most of them have very similar rate dependencies, almost about first order on this, except for example, formate, which has a little bit higher rate dependence. So as we pressurize systems, let's say if we want to pressurize the CO2, we would start to expect getting a little bit more formate, everything else being equal. And then if we look at really the potential dependency, if you will, we see that most of the products are basically roughly the same in terms of a dependence on the alpha. But what we see here is really the hydrogen and especially the methane are very different. And so as we start to increase potentials, we're going to start to favor some of these products over others. So what we can do is use this kind of information and use it before in our model, and we'll do that first, of looking at a product distribution. And so as I mentioned, because we have porous electrode effects, because we have those transport of CO2, because we have the transport of ionomers, we are going to get differences. And so this is looking at a 1 micron catalyst layer versus a 10 micron catalyst layer. Nominally, these have the same amount of kind of loadings such that the overall geometric current density is very similar in the two cases. What we can see is the product distribution is not the same. And this product distribution, as we just saw, is going to be a function of the cell voltage, as well as the cell location if we plotted it that way. And so what you can see is very close to the membrane. Perhaps we're actually going to get a lot more hydrogen and a lot less C2 products. But really to highlight the fact that these porous electrode effects, so if we want to take a 1 micron being right next to the membrane, even in the 10 micron case, we can then see how they're going to shift as we move through the catalyst layer. And that's due to the fact of all this transport and these interactions very local. So as we saw before, there are ways to perhaps levers to control these kind of systems. And so is there something that we can get better than just kind of this bulk type analysis and bulk results? And so finally, what we did is looked at something called pulsed electrolysis, where actually what we're going to do is pulse the system. And so shown here is we're providing potential pulse between kind of a less cathodic and more cathodic potential. And we're just going to pulse this at some rate. This is going to go to, if we look at it versus SHE versus RHE, we have slightly different dependence. That's just a pH type of thing. But if we look at what we would expect for the pH, we would expect enhanced pH when we simulate this kind of effect. And we would expect simultaneously enhanced CO2. So ideally, this should get us more of these C2 plus products. We have high alkalinity, high pH, but also high CO2, at least temporarily. And so shown on the right are both the static simulations as well as the static experimental data for the first two columns, and then the pulse. And so one, we see that the model, and just using those simplified kinetics, actually captures a lot of these trends very well. We see that it captures things like the overall current density, which are relatively low. This is in a planar DEM system, so that we can actually figure out what the actual products are, relatively straightforward. But we can see is when you go from a static case to a pulse case, you really start to reduce the hydrogen that's coming off of the system. And that's due to the fact that you have kind of this high pH that occurs, such that the pulse pH is relatively higher than the static pH. But as well as you also get more of the ethanol and C2 plus products compared to even the C1. And that's due to that enhanced CO2 rate that's driving that. And so this is one way to kind of control it. We can look at the separate breakdowns. Here you can look at the hydrogen currents versus the C1, the C2 plus, and the total current density distributions. And so once again, highlighting that the C1 products are suppressed, and then that spike increases the CO2, and that CO2 allows us to do more of the C2 chemistry. And so this is a case now where we can actually use dynamics to reach a metastable state, if you will, that we can use to get the products that we want. And something that wasn't actually seen before when we just do static type experiments. And really, this is not changing the catalyst in any fashion. This is only changing the reactants and the local environment of the catalyst. So it's really the transport is what's controlling all of these changes more so than the actual catalyst itself. And so similarly, then we can say, well, we have a model of the system, let's do some optimization. And so we can do things like figure out which peak and pulse width that we actually want. Not too surprising, we want smaller and smaller pulses in order to kind of capture these peaks. Obviously, there's going to be other phenomena at the very short time scales that won't allow us to do that, such as double layer charging, capacitance effects. But at least within kind of, we believe we can, 5 seconds is okay. Or 10 seconds is what we saw for most of the other work. And then similarly, we can look at the pulse shape and specifically the potential distributions. And this one's a little bit interesting because now we can go back to those chemical formulae, and we saw that methane was much more sensitive to potential. And because of that, there's going to be an optimum here in terms of we want to not increase too much methane. We want to make this ethylene and ethanol, these C2 plus products. But we actually don't want to go, too much to the static case either, where we don't really have enough of a change to cause that CO2 change and to cause that pH change. So on those two different levels, we can actually see that we can get an optimum here now using the model in terms of the peak shape and the potential distributions that we want to do. Once again, trying to control that transport throughout the system. So in summary, what I tried to show through those kind of case studies is really, we're using porous electrodes in a lot of different types of technologies. They're very amenable towards things like high rate processes. But because we're at high rates and because of some of these other effects, we really want to understand the transport. And so it's really the transport that's playing a very primary role in terms of performance, and especially local transport to the reaction site. So of course, we do worry about transport, multi-phase flow, and other limitations that can occur. But really, whether it's in the fuel cells at low loadings, whether it's in the CO2 reduction, it's really getting it to that reaction site and those interfaces. So that could require things like new materials, new integration schemes, new operation schemes like the dynamic pulsing. Water management in general and any of these fuel cell-like systems is going to be very critical because these polymers depend on water to conduct efficiently, but also because water is a reactant in the system. When we go to alkaline systems, it's both a reactant and a product. When we look at membranes, they have very large electroosmotic coefficients and a lot of transport processes. For CO2 reduction, and I think most manufacturing, these exchange GDEs are very promising, but we really need to understand the overall CO2 transport. And that's due to the fact that you can get kind of this loss of CO2 if you're too alkaline. And also the way the transport can actually induce, especially for the porous electrodes as well as locally, different selectivity and rates. So with that, I'd just like to acknowledge my group who worked very well in the pandemic, at least virtually. There have been a lot of students over the years, some that are still here, some that have left, but have contributed to kind of this research that was all kind of stemmed out of kind of different funding from different funding sources shown here on the bottom. And with that, I'll take any questions.
Please go ahead and ask any questions after the speaker. I'm going to be monitoring the questions in the chat.
I can start asking questions. I don't know if I'll be audible in the recording.
I don't think so.
Okay, that's
there's
fine.
no choice.
Yeah, Adam, great talk, like lots of stuff to process, and thanks for pitching up the importance of transport. I mean, it's so important to consider it. So thanks, kids. I mean, I have a couple of questions. One is like very basic, like the gas diffusion electrodes. Like, what is the typical morphology? How are they made? What materials are used? Could you do something to the morphology of the GDE to even more control the boundary layer to be smaller, or would you do something on the flow side of the gases to get it to be smaller to support large requirements? Like, just what are your?
Yeah. So the question is on the gas diffusion electrodes. So these are typically. Let me go all the way through. No, typically carbon papers, or in terms of electrolysis, porous titanium or sintered titanium. It's really to be very macroporous, distribute gases or electrons, take away water, vice versa, depending which way we're operating. In terms of the catalyst layers themselves, these are typically, composed. These are, roughly, 10 micron type layers. Shown here, they're typically composed of some catalyst particles around 40 nanometers or so that are mixed with these ionomers into inks and slurries in kind of a different solvent system, and then are either roll casts, for example, or slot die if you're trying to manufacture. Spray coating is what we would typically do in the lab and kind of put them down. There has been work on, especially, are there different architectures, such as if we see ionomer as a problem, people made things like ionomer pillars and arrays, and then impregnated the catalyst inside those to kind of provide highways for ions and then off ramps to the catalyst sites. People have looked at nanostructured catalysts themselves as well. Like I said, on the fuel cell side, we've looked at, instead of carbon supports that aren't porous, looking at very highly porous carbon supports. Those have other effects, but they can actually show better performance, more surface area without as much poisoning. And then, of course, there's been gradations of things like porosity that people have explored as well. I think within the gas diffusion electrode, especially when we start looking at CO2 reduction and the dependence, the spatial dependence, and maybe the temporal dependence as well of the products, there's an opportunity there to kind of optimize them even further.
And just one allied question there would be, you talked a lot about the local current density on the catalyst particles themselves having an impact on the potential distribution. Would you also try to change the size of the catalyst particles? Like, is that tractable to do, or from a manufacturing perspective, you just get like one size distribution that you kind of have to?
No, I mean, you can do multiple sizes. The question then would be, how do the aggregation physics happen in terms of, do they always aggregate to the same size?
No.
There's a lot of things like sonication that happens to break up particles before you're actually doing any of the coating type mechanisms. There's different drying rates that we can actually put as well to create different structures. But you can definitely look at different catalyst areas. I mean, typically we're trying to go small as possible because they're really just a reaction site. So this is the opposite of like a battery, where it's also an intercalation site, and you want kind of bigger particles too.
There's probably a size optimum.
Yeah, there's always an optimum of everything.
Okay.
Got a couple questions here.
Yeah.
You want to read the question so everybody else can hear and then answer? So this is the first.
Which one do you want to start with? So do you anticipate that the heavy duty fuel cell trucks can compete economically with e-fuels to fuel heavy duty IC engines? Does not seem like they will compete with heavy duty IC engines running biofuels, but biofuel productions will be limited. So if we look, there's always a trade-off, when we go to larger scales. And so what we see is, if we look at the predictions for long haul trucking, we don't see full electrification getting there. And that's because of, recharge rates is recharge times or charging times, as well as the fact that fuel cell systems, like any engine, are going to be a separation of power and energy. And so you get benefits the more larger you go, because unlike a battery, you're not adding extra end plates and everything else if you want further range. In terms of, we look at the cost targets of hydrogen and we look at the cost targets and projections for the fuel cells, it actually seems pretty competitive with something like biofuels, especially with things like anti-idling laws that are going to come into place as well, because the fuel cell can provide that electrical power as kind of a generator. So we actually see, them actually being pretty competitive. We think that will actually, could be possible for the future. The other question was, could you please comment on flow field designs, microchannel and bipolar plates for various microreactors like hydrogen fuel cells and flow batteries? So sure. So flow field design wasn't something that I necessarily talked about as much. For things, it's going to depend a little bit on what you want. So typically you're trying to maximize, the overall penetration of the reactant into the system and minimizing the pressure drops and losses that would be due to pumping. In a fuel cell, that's not much of a problem because it's mainly just gases. And so there you're trying to control a little bit the water management and making sure that water droplets don't cause problems. But typically you're doing parallel channels with maybe some serpentine bends here and there. On the redox flow batteries, because you want the penetration of the liquid electrolyte, you're typically looking at an interdigitated type system. So you kind of a teeth type system, if you will, which will always force some convection underneath the lands to actually increase the penetration depth of the liquid into the system. So it's not just flowing by. And so that's kind of what we've looked at. We haven't necessarily optimized it that much. For a lot of the research that we do, we get feedback that flow field designs are much more proprietary. And since we're a national lab, we're not supposed to be doing any kind of proprietary research. And so we always get pushback from car companies, especially. The other question was, as for the water management, which is more of a concern, the wetness of the GDL membrane or the drainage of water droplets inside the microchannels. Typically in a fuel cell, the inlet humidity is roughly 30 to 40%. The outlet humidity is close to 100%. Besides very low temperature performance, where you might freeze, then typically the water management is more about keeping the membrane hydrated as much as possible. When we talk about, worrying about freeze or something like that, so if you have a car in Michigan in the winter, it will actually blow out the air channels. It's programmed to do that when it reaches a certain temperature, such that it can start up without freezing a lot of the water in the system. And in which case, sometimes then the water droplets start to become more important, but usually once again at the catalyst layer problem. The only time in the channels that it's a real problem is when it creates a huge blockage and a slug, but usually these are designed enough that the higher pressure drops that it causes will actually flush out the channels eventually. So unless you get a real stagnant region, then you're probably fine.
Question.
I was just.
Good.
Yeah. So at one point you were increasing the temperature for the CO2 reduction. Did you see any losses from decreased CO2 concentration in the warmer temperatures, or did you see that masked more by the GDE?
Yeah, so all of these results are done with more or less just saturated water in CO2 pure streams. So sure, as you go towards lower concentration CO2s, you would start to become a little bit more CO2 limited. And then if you go up to higher temperatures, become more limited. If we went up to something like 100 degrees, obviously we wouldn't have any CO2 at all. So we maxed out here at 50, but that's a lot because of the stability of the polymer itself. And a lot of these polymers are stable up to 50, maybe to 80 if you get lucky. Just as reference, fuel cells typically operate roughly around 80 degrees, but they're typically also pressurized to 150 or 250 kPa. And so you don't get kind of the limitations on the oxygen or hydrogen that you would get if it was just ambient. But it's a good concern.
Good questions. I can ask one. With regard to this issue of sort of CO2 starvation because of alkalinity, are there pathways or ways you can go from carbonate or bicarbonate sort of at the interface to some useful product, or are you just stuck if you're at bicarbonate or carbonate? Maybe
Sure.
you do some sort of game where you acidify it and then you get like a high local concentration of CO2. Like, can you play with that, or is it?
Yeah, so I mean, I can answer that. One is it's our belief that there is no carbonate to like ethylene route, right? It has to go through CO2, probably has to go through CO. But what you can do is you can use things like whether you have a way to create local acidity, you can definitely do that to generate the CO2 from carbonate. So Curtis Berliget's group, for example, has recently published where they used a bipolar membrane. So it's something that is both a proton conducting layer and an anion conducting layer. And what they did is just fed in seawater. And at the interface of the two, at the interface of the bipolar membrane, they generate a whole bunch of CO2. And then you can watch, they have a movie of the CO2 bubbling off, but then that CO2 goes back and reacts. And so you're never feeding CO2 in that system at the macro scale because it generates it itself. I would think that you could do something very locally too, to create the CO2. The problem is going to be you have to make sure that that local acidity doesn't just create a whole bunch of hydrogen.
I have one more.
No time.
I think there's another one.
The pulsed electrolysis is interesting. Do you think like at larger scales that would be a viable kind of operational strategy, or what kind of like challenges? Or I mean, it seems like the shorter the time scale, the better it is, because you kind of accumulate locally the CO2 in that sort of little region, and then you're talking up the rates and selectivity. So, what do you anticipate having challenges if you want to scale it up to a larger system?
Yeah, so on the pulsed electrolysis, I mean, there's a few things. One, if you look, it was a low current density result. And so we have to make sure that it agrees when we have these larger concentration gradients at higher current densities. But pulsing itself is scalable in terms of, if you look at Faraday Technologies as a company, for example, that their whole thing is pulsed electrochemistry. And that you can do that at very large scales, right? The electronics is very fast compared to reactions and things that we worry about. But I'd worry then about, whether it's, once again, since it's very local, we don't worry so much about diffusion and those kind of processes. But really, if we want to do that on top of a high current density, then that's going to necessitate some more engineering and some more thought. There's a question also on high temperature fuel cells as a possible future trend. Yes, I mean, so if we create a membrane that doesn't need humidification, that would be kind of a game changer, right? We want to operate fuel cells at roughly, 200 degrees or a little bit lower, right? So a lot of fuel cells, because we have to operate below 100 degrees, the heat transmission out to the environment actually ends up becoming what's limiting us. So if you look at a Toyota Mirai, they have twice as many radiators as a normal car. If we look at trucks, we're still going to need a lot larger radiators too. And so that's where we're going to start pushing to wanting to operate at higher temperatures. If we're talking, things like solid oxide cells or even solid ceramics at higher temperatures, those can definitely play a role, especially in, a lot of the manufacturing. The transportation applications, probably not. Vibrations and ceramics don't go very well together. And also the startup time and shutdown time. We have one project that my colleague Mike Tucker has looking at, for Nissan, using it as a range extender, a solid oxide cell. In that case, he uses a metal supported cell. And so that can basically take all of the thermal loads without cracking, unlike a traditional cell. But we don't necessarily see that as being primary propulsion in terms of the size. But definitely, high temperature processes get rid of a lot of the catalytic issues that we have in the low temperatures and some of the transport issues too.
Let's see if that answers the question. Time for maybe one more question. Okay, well, it's 5 p.m. So thank you all for coming. Let's thank our speaker, Dr. Weber, once again.
Thank you.